Welcome to the pH scale. So we already talked a little bit about acids and bases and how to identify them. We've talked about the strengths of acids and strengths of bases. So now let's look at one way of measuring the acidity or basicity of a solution. So if we look at a neutral solution of water, we know that because of the autoionization of water, Kw, our ion product constant, is equal to hydrogen ion concentration times the hydroxide ion concentration. And at 25 degrees C, this is 1.0 times 10 to the minus 14. So if our solution is neutral, then our hydrogen ion concentration has to be equal to the hydroxide ion concentration, because if we have a neutral solution, then we have no acid or base around, and the only source of each of these is the autoionization of water, so they have to be equal. So then the hydrogen ion concentration is equal to the hydroxide ion concentration, and that means that in our expression here, if we replace Kw with 1.0 times 10 to the minus 14, that has to be equal to the product of our two concentrations, and now we can replace the hydroxide ion concentration with the hydrogen ion concentration because they have to be equal, and that means that now we have 1.0 times 10 to the minus 14 is equal to our hydrogen ion concentration squared, and then our hydrogen ion concentration is the square root of 1.0 times 10 to the minus 14 molar squared, which gives us 1.0 times 10 to the minus 7 molar. So in a neutral solution, the hydrogen ion concentration is going to be 1.0 times 10 to the minus 7 molar. The hydroxide ion concentration will also be 1.0 times 10 to the minus 7 molar because we know they're equal. So here, even a strong acid at high concentration only gives us a hydrogen ion concentration of around 10 molar or so. And that's rather concentrated. So this means that most of the time our hydrogen ion concentration is going to be small. It's going to be significantly less than 1. And we want some way of shortening our concentrations like 1.0 times 10 to the minus 7 molar to something shorter. So this is where we use pH. So pH, the P there stands for power of, the H is hydrogen, the hydrogen ion concentration. So pH is the power of hydrogen. This is equal to minus log base 10 of the hydrogen ion concentration. Note that we really can plug anything else in we want here for H. We can have POH. In that case, it would be the power of the hydroxide ion. And so we'd have minus log base 10 of the hydroxide ion concentration. So for a neutral solution, then the pH is equal to minus log base 10 of the hydrogen ion concentration. In a neutral solution, remember that the hydrogen ion concentration is 1.0 times 10 to the minus 7 molar. And that means that we have minus the log of 1.0 times 10 to the minus 7 is negative 7. So we have negative 7, which is a positive 7. So the pH of a neutral solution is 7. And note here that pH is a logarithmic scale because we're taking the log of our hydrogen ion concentration. So that means that if we make some change in our pH by a unit of 1, that means that our hydrogen ion concentration is changing by a factor of 10. So if we go from 7 to 6, that means that we've changed our hydrogen ion concentration from 10 to the minus 7 to 10 to the minus 6. And our hydrogen ion concentration then is 10 times what it was before our change. So that means that changes in pH from, say, 7 down to 1, that's 6 orders of magnitude. That's 6 pH units. That means that our hydrogen ion concentration is 1,000,000 times higher than it was when we started. So that means that that's the power of our logarithmic scale here. So most of our pH values fall between 0 and 14. The pH can be negative, or it can be above 14 if you have a really, really concentrated acid or base, and that acid or base is a strong acid or base. So again, a pH 7 is neutral. pH less than 7 is acidic because now the hydrogen ion concentration is more concentrated than it was when it was neutral. A pH greater than 7 is alkaline or basic because now the hydrogen ion concentration is less than it was when it was neutral. Again, we can use other P scales So here, the P of some quantity is equal to minus log base 10 of whatever that quantity is. Again, there our P stands for the potential of, and so sometimes it's useful for us to describe a system in terms of the hydroxide ion concentration using POH. So POH, again, is equal to minus log base 10 of the hydroxide ion concentration. So if we want to calculate the POH for a neutral solution, we have hydrogen ion concentration equal to hydroxide ion concentration. We know that the Kw is 1.0 times 10 to the minus 14. That has to be equal to the product of our two concentrations. If we replace our hydrogen ion concentration with hydroxide ion concentration, we then get 1.0 times 10 to the minus 14 is equal to the hydroxide ion concentration squared. And then we know that when we take the square root to find our hydroxide ion concentration, we have the square root of 1.0 times 10 to the minus 14, which gives us 1.0 times 10 to the minus 7. I hope this is familiar for you now. And then the POH is equal to minus log base 10 of 1.0 times 10 to the minus 7 molar, which gives us negative 7, which is positive 7. So again, the POH of a neutral solution is 7. The pH of a neutral solution is 7. So if we have POH equal to 7, we have a neutral solution. If we have a pH greater than 7, POH greater than 7, it's an acidic solution. If the POH is less than 7, then it's an alkaline or a basic solution. So as the P quantity is getting higher, that means the concentration of our quantity is getting lower. As the P quantity is getting lower, that means that concentration of our quantity is getting higher. So as pH gets lower, we're getting more hydrogen ions around. As POH gets lower, we're getting more hydroxide ions around, and thus fewer hydrogen ions around. So if we want, we can show the relationship between pH and POH, because we know Kw is equal to the product of our two concentrations. We know that that has to be equal to 1.0 times 10 to the minus 14. If we take minus log base 10 of each side, we get minus log base 10 of Kw, and that's equal to minus log base 10 of the hydrogen ion concentration plus minus log base 10 of the hydroxide ion concentration. And we know that that then has to be equal to minus log base 10 of 1.0 times 10 to the minus 14. That means that here we've got minus log base 10. Let me erase that mark. We've got minus log base 10 of our quantity Kw. Well, that means that it's the P of our quantity Kw. So that's pKw. That's equal to pH plus POH, because this is the pH and that is the POH. And we know that minus log base 10 of 10 to the minus 14 is positive 14. So that means that POH is equal to 14 minus pH. pH is equal to 14 minus POH. And that pKw was equal to 14. So when we want to measure pH, the most accurate method we have is to use a pH meter. But there are some other substances that change color as pH changes, and we call these substances acid-base indicators. Sometimes we don't want to have to pull out a pH meter, or we don't have one handy, and so we can use an indicator to give us a rough idea of what the pH is. Again, if we want to know more than just, is it about 6 or is it about 7? If we want to know, well, it's 6.05, then we need to use a pH meter. But if we just want to differentiate between 6 and 7, we can do that using some indicators. So again, our indicators are changing color over some relatively narrow pH range, and this makes them good for telling us whether the pH is above or below some value. But again, they're less precise than our pH meters are. So that was the pH scale.